in a similar way, one can go about testing for the variance of a normal distribution. Now, once again we have seen here that the variability of the normal distribution was tested in the Neyman-Pearson lemma setting by sigma x I square. That means, how much the value of sigma x I square is becoming, is it more or less kind of thing. So, when we consider the composite hypothesis for sigma square, we will be basing the decision on the distribution of sigma x I square. As we know, the distribution of sigma x I square by sigma square is chi square. So, we will actually be getting a chi square test. So, let us consider two different cases testing for the variance. When we are doing the testing for the variance, let us write down the model here. Say mean is known, say mu naught. So, we are having x 1, x 2, x n following normal mu naught sigma square. So, if we go back to the setting of normal 0 sigma square, we can actually consider x I minus mu naught square. So, summation of this, that divided by sigma square, that will follow chi square distribution on n degrees of freedom. So, we may look at the hypothesis of the form, say h 1 sigma square less than or equal to sigma naught square against say k 1 sigma square is greater than sigma naught square. So, when sigma square is equal to sigma naught square, we may consider sigma x I minus mu naught square by sigma naught square. So, this will follow chi square distribution on n degrees of freedom when sigma square is equal to sigma naught square. So, we may use the test as reject h naught if w is greater than or equal to chi square n alpha. The similar argument will be valid if I am considering sigma square is equal to sigma naught square against sigma square is greater than sigma naught square. So, if we consider carefully, then the reverse of this, say sigma square is greater than sigma naught square against sigma square is less than sigma naught square, then the test will be reject h naught if w is less than or equal to chi square n 1 minus alpha. The same test will be valid if I use sigma square is equal to sigma naught square against k 1 sigma square is less than sigma naught square, because what we are saying is sigma square is less or more, and therefore, this is going to be useful here. Let me take one example here. Suppose the value of, suppose we are considering say x 1, x 2, x n following normal 0 or we may put say 5 sigma square, and we are observing here sigma x I minus 5 square is equal to say 10. We are testing the hypothesis, say h naught sigma square is equal to say 4 against h 1 say sigma square is equal to maybe 10. So, if we look at the value here w, that value will become equal to 2.5, that is sigma of x I minus 5 square by sigma naught square, that is 4, that is equal to 2.5. Now, we have to compare with the chi square value on, suppose I am taking n is equal to 5, then this I have to see chi square 5 at alpha, suppose I say alpha is equal to 0.05. So, from the tables of the chi-square distribution, one may look at chi-square 5.05 as equal to 11.075. Naturally, you are getting W to be less than, since we are testing here. So, we may put here greater than or equal to 4, say this is equal to 4 and here greater than 4, suppose I am putting. So, the test is to reject for larger value. So, here W value, that is 2.5 is less than chi square 5.05. So, you can see here we cannot reject H naught at level alpha is equal to 0.05. Let us look at the interpretation of this. We are testing about the variability here, that variability is equal to 4 or more than 4. Now, what is happening here is that sigma x I minus 5 whole square, that is turning out to be 10. So, if we look at sigma x I minus 5 whole square by 2, that is by n, which is the maximum likelihood estimator, that will be equal to 2. So, if we are using that as an estimator, naturally it is less than 4, that therefore, sigma square greater than 4 is not supported very much, and whether it is significantly not supported, that we have to see from the probability of the type 1 error, and here it turns out that actually we cannot reject H naught. Now, let us consider the case of when mu is unknown. When mu is unknown, we cannot make use of W. In place of that, we have to make use of the distribution of S square. So, n minus 1 S square by sigma square follows chi square on n minus 1 degrees of freedom. So, let me call this statistic W star as n minus 1 S square by sigma square, sigma naught square here. So, if we are testing the hypothesis, say of the form, say H naught sigma square is say less than or equal to sigma naught square against say H 1 sigma square is greater than sigma naught square. So, what will be the test function? Reject H naught if W star is greater than chi square n minus 1 alpha. Suppose we are looking at two sided hypothesis, sigma square is equal to sigma naught square against say H 1, sigma square is not equal to sigma naught square, then the test function will be, the rejection region will be W star less than chi square n minus 1 minus alpha by 2 or W star greater than chi square n minus 1 alpha by 2. Let us look at the examples here. So, we want to test the hypothesis whether the sigma square is equal to 1 against sigma square is greater than 1. So, a random sample of size 25 is taken and it yields S square is equal to say 5 50. So, if we are considering say n minus 1 s square by sigma naught square, then this value turns out to be 24 into 50 divided by 1, that is equal to 1200. You can easily see that this value is extremely large, because s square is actually used as an estimate of sigma square, and this value 50 is much bigger than 1. Therefore, at any level of significance which is practical, the value of chi square will always be much smaller than 1200. On the other hand, suppose I am considering here the sample which gives say s square is equal to, in place of 50, its value is turning out to be say something like say 2, then there is a change here, because then the value of n minus 1 s square by sigma naught square in that case will become simply equal to 48. Now, if we are looking at the tables of the chi square distribution, one may easily observe the difference, because chi square value, and if I am looking at say 24 degrees of freedom, and here at a certain level of significance after 0.05 the value will cross this one. So, in fact, with little luck, suppose I am taking say s square is equal to 1.5, then what will happen? Here n minus 1 s square by sigma naught square would become equal to 36, and here you can see even at say 1% level of significance the value is 36.19, and therefore, we will not be able to reject H naught here. So, easily you can see that the acceptance or the rejection of the null hypothesis is dependent upon the probability of the type 1 error as well as the point sigma naught square, or you can say theta is equal to theta naught in the null hypothesis that is used as a control here. If we are considering say two sided here hypothesis, in that case we may have something like say H naught sigma square is equal to say 2 against say H 1 sigma square is not equal to 2. Now, in this case what will happen? Suppose I have observed say s square is equal to 2 itself. Then if I have considered a sample of size n is equal to say 11, then you will have n minus 1 s square is equal to 20. Now, you look at chi square value on 10 degrees of freedom say at 0.05. Now, this value chi square 10 at 0.05 is equal to 18.30. So, here if I am considering say level alpha is equal to 0.1, then you are seeing that your W star is greater than chi square n minus 1 alpha by 2. So, H naught is rejected. Now, you may slightly wonder here that s square was 2, sigma square is equal to 2, even then you are rejecting this. The reason is that for the sample of size 11, if you are getting this value, then there is a slight discrepancy, because chi square on 10 degrees of freedom is giving you a value which is slightly smaller than this, that you are getting 18.30. So, this is even turning out to be in the rejection region. So, even a smaller value than this would have been supported here. Now, in the one sample problems we may consider tests for proportions. So, the setup is that we are observing a sample from a Bernalian trials. So, we may consider the sum, and we have a setup like x following binomial NP distribution, and we may be interested in testing about say H naught, say p is equal to p naught against say H 1, p is not equal to p naught. Now, here we have seen we may consider the test statistic based on x, because the distribution of x is binomial. So, if we consider x minus n p naught, so we may divide it by this. So, we are dividing by p here. So, p is equal to x by n. So, if we consider the value here to be p minus p naught divided by root p naught q naught divided by n, then we can use it as a test. On the other hand, one may use here the estimates of this also, p minus p naught divided by root p q by n, where p is this, q is 1 minus p. So, one may use either of these things, and when n is large, one may use normal approximations and the test is reject h naught if z alpha by 2. Let me consider an example here. Suppose a random sample of 500 customers was considered, and here x is observed to be 41. Let us look at say p head and q head here. So, p head turns out to be 41 by 500, that is 0.082. So, if we consider p head q head by n into say z 0.025, suppose I take alpha is equal to 0.05, then this value turns out to be 0.024 say. So, if we are considering here the confidence interval, say 95% confidence interval for p, then that will be equal to 0.058 to 0.106. So, easily you can see, suppose I am testing here the hypothesis h naught p is equal to say half against h 1 p is say greater than half or p is not equal to half, then naturally h naught will be rejected. You can easily see here the value is actually lying between 0.05 to 0.1. So, if I am testing the hypothesis p is equal to half, then naturally it is will be rejected. On the other hand, if we are considering the hypothesis say p is equal to 0.05 against h 1 p is not equal to say p is greater than 0.05 or p is not equal to 0.05, then this will be accepted. This h naught will be accepted at 5% level of significance. Let me take one more example here. The differences in tensile strengths of 5 pairs of rope were measured, and the observations are -2, -3, 1, 0 and 1. We want to see whether the measurements are unbiased, that means the differences are significant or not. So, if you consider these values to be say x i's, we may consider the model x I follows normal mu sigma square, and the testing problem becomes for I is equal to 1 to 5 h naught whether mu is equal to 0 or h 1 mu is not equal to 0. Now, you see we need to calculate the mean etcetera. So, x bar is equal to minus 0.6 here, say standard deviation turns out to be 1.81, say 82. So, we need to look at root 5. Since I am taking mu is equal to 0, then the test is about minus 0.6 divided by 1.82. Easily you can see, suppose I am seeing the value of t at say 0.025, that means I am making a test at level of significance alpha is equal to 0.05, then this value is 2.776. Easily you can see that this value is less than this. Sorry, if I am taking absolute value of this is less than 2.776. So, we cannot reject H naught. That is also supported by this, because here you are having two values which are slightly negative and one value is equal to 0 and two values which are slightly positive. So, here you can see that if I had calculated a 95% confidence interval for mu, then that would have included this value here. Now, this idea of the extension of the Neyman-Pearson lemma to composite hypothesis can be applied to other distributions as well. Suppose we are taking the example of say exponential distribution that we considered, that x 1 x 2 x n following say exponential distribution with parameter lambda, and we are testing say hypothesis lambda is less than or equal to lambda naught against say lambda is greater than lambda naught. We had already seen the interpretation of the lambda here, which is the reciprocal of the mean. So, we had seen that for the larger value of the mean, larger value of the sample mean, we will be having a smaller value of the rate, that means, we will tend to accept H naught, and for a smaller value of the mean, we will be tending to reject H naught, that means, tending to go in favor of H 1. And the test function we had devised in terms of a chi-square distribution, because we had made use of sigma x I. So, we considered twice sigma x I. So, if we consider twice sigma x I divided by lambda naught, then if let me call it W, then this will follow chi-square distribution on 2n degrees of freedom when lambda is equal to lambda naught. So, the test function will be to reject H naught when say W is. So, since W is favoring 1 by lambda higher value, so smaller value of 1 by lambda will become corresponding to less than or equal to chi square 2 n 1 minus alpha. Let us just take an example here, where sigma x I turns out to be say 10. We are testing about say lambda naught is equal to say 2 and say n is equal to say 5, and say then this test statistic could become equal to sigma x I. So, W will become equal to twice into 10 by 2, that is equal to 10. Now, if you look at chi square value of 10 at say 0.95, then from the tables of the chi square distribution, this value turns out to be equal to the value of the chi square at this will turn out to be at 10 degrees of freedom, if we look at 0.95 value is 3.94. So, easily you can see that this W is bigger than this chi square 10.95. So, H naught cannot be rejected at 5% level here. Here lambda naught is 2, and if I am considering a natural estimator for 1 by lambda, that will be equal to x bar, that is equal to 2. So, that value is not significantly different from this. So, we are testing whether this is less or not. So, then that is not supported by the data here. In the forthcoming lecture, we will be considering when we are comparing two populations. So, we will be discussing tests for the differences of the means or the ratios of the variances for two normal populations, as well as we will take up cases for comparing the proportions of two binomial populations. We will also look at the chi-square test for the goodness of fit, etcetera.